Welcome to the beginning of classes. For how many of you this is the first class in the term? All right, well, happy start of the semester. So my name is Patricio Mendez, and I'm gonna write it here. Ooh, not with this one. So let's see. I'll be your instructor in this class. And let me tell you, you're up for a treat because this is an awesome class. You're gonna get to do hands-on welding. You're gonna get to learn some theory. You're gonna meet people from industry. You're gonna have fun. Hey, you're even going to get credit. So it's all good. So we're going to start like pretty much full on with the class. I already uploaded the material. I believe all of you likely checked the eClass website, right? So everything's there. We're gonna keep updating it probably before each lecture. Things might be slightly updated. So this is what I'd like to do today. How about if I tell you a little bit about me, the lab, the welding program at the university. You have no escape, so I'll talk about me. But then I'd like to know a little bit about you. We can talk about the logistics for the semester. And I'll try to do this relatively quick. And then I'd like to start a discussion about if you sign up on a class on welding engineering, what the hell is welding engineering, right? And what I tell you might be an eye-opener of some things that maybe either you didn't know or you didn't think before, or you thought you knew them, but you see them in a new light. So I'll start telling you a little bit about me. So I'm Argentinian. The charming accent is from the city of Buenos Aires, way down here, in the other end of the world from Canada. And so when you meet a new group of people, you try to establish credibility. I have the whole semester to establish credibility through my knowledge. But right now, you don't know if I know anything or not. So I'm going to establish credibility by association. So I'm going to tell you I'm close to the best soccer player in the world, which is Messi, and it's not Cristiano Ronaldo, and it's not Neymar for sure, right? Argentinians are people close to God. This man here, you might know, that's a Catholic Pope. He's very close to God. Actually, he's right next to God. This is God, right? We all yeah, exactly. And this fancy lady here, I have shown these photos so many times, and not once anybody knew who she is. And Ale, you cannot say anything. He's the one who would know. Anybody knows who this lady is? Sven? Well, that means you don't read enough glossy magazines, which means you're in engineering. And this is the Queen of Holland, the Queen of the Netherlands, right? And she's from Buenos Aires, and she has the same charming accent. Maybe she has other charms too. I don't have, but that's okay. So you see, if at the end of the semester you're not convinced about knowledge, yeah, at least I have some good associations here. So I'm a mechanical engineer from the University of Buenos Aires. My specialization is in machine design. The undergrad I had, what you would call an undergrad, it took me 8 years to do. It's a very long program. I had 6 semesters of calculus, 4 semesters of linear algebra. I had 5 semesters of electrical engineering. I had 5 semesters of physics, right? It's a very different program than here. And I also did research in the 80s on wind turbines. Like what nobody cared about wind energy. That's me hanging out from a wind turbine, supposed to be in the middle of nowhere, right? That's in the 80s. Now everybody's doing wind turbines, but I saw the light and I do oil and gas. Huh? So I also worked at a company, Tenaris. Tenaris is a very big multinational company, but it originated from Argentina. It has facilities even in Edmonton, right? It's over Canada, all over the place, the US, Europe, Asia. And they are still makers. And because I'm a machine designer, I was designing testing machines. I was involved in designing this machine. It's a crazy thing. It's a tensile test machine, a servo-hydraulic testing machine, but you can buy them. But we didn't have the money to buy them. But we had so many people who were so cheap, we designed it from scratch and we built it. And it worked. And I designed this contraption here for doing wear testing. I was in Argentina about 5 years ago, and that is 21 years after I had left Argentina. And they were still using this machine. And the star product of this company, Tenaris, is a special lubricant for threading pipes when you're doing downhill. Sometimes the pipes downhole, you thread the pipes, and you use special greases so it doesn't go. And they started developing this machine. I'm pretty proud of that. So at least once I did something useful, right? And that's one more than most professors can say. So from Argentina, I had a dream of study abroad. It's a funny thing. I didn't know if I wanted a master's or a PhD. I didn't know if I wanted in Europe or in the US, but it's the good luck of God that I landed at MIT in Boston, where I did my master's in what is called semi-solid metal processing. I'll show you more about that in a second. I did my PhD on welding at high currents. When I talk about welding right now, it might not make a lot of sense to you, but you're going to see at the end of the semester, you'll wish you knew everything you know then. You'll make sense when I say welding at high currents and what that means. I did my postdoc on mathematical modeling, all those at MIT. I was at MIT for, what is that? 9 years. I had an affiliation for 11 years, but for 9 years I was living there. I had a startup too. In the startup, we invented a machine as students. That's crazy. In the mid-90s, everybody was starting internet companies, but we invented a machine to make car parts, and the car parts were in the Ford Focus. So every Ford Focus of the vintage of 98 to 2002 has this part called the fuel rail that is part of the engine, done in our machine. And here is the machine we built. Here's the patent drawing, and was good. At one point, I thought I was going to be a millionaire. And if you're a millionaire, you have a problem, because how do you find somebody who loves you for who you are and not for your money? But the problem got solved. I'm sure my wife loves me for who I am and not my money. And I was a consultant too for 2 years. But that wasn't my cup of tea. But I was making real money here. I was single. I didn't know what to do with my money. And again, I have a way of solving money problems. So now the funny thing, we made this part to make this machine to make car parts. But that's not what we wanted to do. The first thing we wanted to do was what at the time was called rapid prototyping. Today you call it additive manufacturing. So look at this video. We are making a metallic part, right? Additive manufacturing. No subtraction, no machining, right? No molds. We're making this metallic part. Now, if you look at the date of the paper, 1994, the date of the patent, 1999, right? The date of our paper in 2000. The patent expired by now. So go crazy and use it, right? We were there, much like I was doing wind turbines before anybody else. I was doing this additive manufacturing. It was called rapid prototyping, but back then. And people said, oh, you don't have enough resolution like a lathe. Now, you have all these monkeys doing the same thing that it looks even worse, right? But I'm already onto something else, right? Like, look, these things, this looks exactly the same. They are trying to use semi-solids here. This material here is semi-solid. You see this joint here? Super important. This was the topic of my master's. They were trying to show the same here. 2017, what is that? Like 20 years late only, maybe more. That's okay. So then after my stint in Boston, I became a professor in Colorado. And at the beginning, I thought being a professor was very stupid. You work so much. When you want to have your papers published, you have to pay to the journals. I still think it's stupid, but I decided I wanted to do it. And I became a professor in Colorado. I was involved in welding and casting research. So I was in charge of a foundry. It was a huge foundry. It was one of the two largest academic foundries in the United States. So it was lots of fun. I like riding bicycles. And that's me, that's Mount Evans. That's the highest paved road in North America. I did it twice, one with training, one without training. It took me about 6 hours. And I used to think it's bad, but this year I did a Jasper to the ice fields, and I was 8 hours on the bicycle. And it takes some quite to get used. Now, that was Colorado. I was there for 4.5 years, learned something about metallurgy. But then I was tempted to come to Canada and start a welding research lab, plenty of chairs, from scratch, the way I thought would be right. And that's an incredible opportunity. If any of you ever have an opportunity to start something from zero and do it right. So maybe if I was stupid, it would go super wrong. But maybe I'm not so stupid because it went very well. And I went from being this guy to being this guy. Now, this is this year, and in the winter, that's my record so far, minus 32 on the bike. For those of you who know some metallurgy, the bicycle is very likely to be below the transition temperature. So if I fall, it would shatter like glass. We created this lab that is an amazing lab. Has so many good things, but one interesting thing is so international. You see all these people here from different countries. And I'll show you another slide with more, right? We had a particular take on welding. So what you're going to learn in this class is not so much how to weld, because there are many places teach it much better than us. And actually, that's not probably what you want. But what is behind welding? So all these companies are sponsoring us. Some put money, some put equipment, some gives us internships. For example, Tesla, right now, we have one of our students doing an internship at Tesla. And we had internships at many of the other companies. Some of you were here when I needed to take a phone call. That's Praxair, that just gave an award to a company on a project that involved one of our former PhD students too. So we're well supported, well loved. Industry has treated us very well and helped us as I teach you theory. I'm also going to pass along some things I learned from industrial practice that I learned from these companies. I don't have that much industrial practice, but they do, and they tell us. About the people, this is our lab. You get to see some more. Here are 10 nationalities, right here, right? And they are not the same as the other photo. We have, I think this is outdated because we have more PhDs now. In 2017, for the ladies here, which are not too many but not too few either, in 2017 we were more than 50% female in the lab. Sven, have you ever reached that?
If it's 2, I'm very lucky.
Yeah. So Professor Sven Goecke here is visiting us from Germany. So it's an honor that you're here, Sven. So. Yeah, and you said 2, you're lucky. Well, we had about 6 or 7, I don't remember. It was a crazy summer. We didn't sustain it. But hey, we still have quite a few ladies involved. We have collaborations that are interdisciplinary. We work on welding procedures, metallurgy, and these things, metallurgy, you know in general. Welding procedures, you don't know what those are. But you're going to see they're very important very soon, and we're going to discuss the physics of welding. That is an area in which we know, and we have a new area on automation. You're going to see all these. This Grammy-looking thing, that's the Image of Welding Award. That's the American Welding Society gives this award to a leading welding education institution. Now, what is special about this, I put it, is the American Welding Society. It's not the Canadian Welding Society, right? But he gave it to us. I never heard that they gave it outside the US. The other thing is when they give it to welding education institutions, they give it to places that teach the act of welding. Well, you're not going to see me with a torch in the class because I'm going to embarrass myself. We don't teach the act of welding, but we teach what is behind so you as engineers can learn more or make informed decisions, right? And again, they had never given that to a university or a higher education institution. They give it to technologists or technicians or trades, right? So we're very, very proud of this. So as you get involved with us through this class, you get to see that, that we are close to industry, despite that during the class you're going to see lots of weird theories, which I hope you'll enjoy as much as I do. We have lots of equipment. We have thermal cameras. We have high-speed cameras. We have, for those of you in metallurgy, we have a dilatometer, an instrumented impact tester, gas chromatographer. Those are in a lab you're going to see when we do a lab tour. We have a very powerful laser unit and many things for characterizing. I'm going to go quick over this, but lots and lots of equipment. Our lab is between $4.5 and $5 million in capital. For industry, that's little. For university, when you typically buy beakers, that's a lot of beakers, right? So we are very fortunate. We have space and we have resources to do almost anything we want, right? We're only limited to by our intelligence and our ability to work. Things we do, and I'm going to show you this slide here, which doesn't mean much to you right now. So at this stage, just look at how pretty this is. But when it comes the first or the second exam, don't remember, you'll be telling me everything about this, right? This is a welding as it's happening, but it's loaded 100 times. This is the way a microscope makes space bigger. This makes time bigger. And what you see is the wire in the weld, the filler metal is melting, and this is the weld. This is molten steel, right? And this is other molten steel coming in. And all these videos look different, right? Just know they look different, but the difference is so important that the welders know it. And you're going to tell me all about it. You're going to learn about this. The welders feel the difference. They cannot explain it. And if they speak about it, very often they don't know what they are saying. But you will know what you say. But still, you should use the welder to weld things of responsibility. You can do the science in which you can coordinate the images and the electricity. And you start seeing how the electricity in welding relates to the heat transfer, to the fluid mechanics, the electromagnetics, all those things, the thermodynamics, happening at the same time. We will discuss about those things. And you'll see that welding is so much more than just a guy with an electrode. We have robotics in our lab. Right now we have 3 robots. You're going to see we have some big projects going, right? This is called weaving. You're going to learn all about that. This is a video from our lab. For those of you in metallurgy, this is a microscope image of a wear-resistant alloy that is based on chromium carbides. You see these kind of hexagons here, right? They're quite mysterious. Nobody really knows how they appear, but we have been doing quite a bit of research on this. But they are very hard, and they are essential in protecting for wear in the oil sands, mining, construction industries, agricultural equipment. This other one that looks very different than this is a tungsten carbide. It's also wear protection. So this is so much more expensive than this other one, and a completely different type of deposition and metallurgy and considerations. Right? We're going to be discussing all the considerations behind which you choose one or the other. This is like cross-section of a weld with the colors are these carbides that precipitated. Here's a guy in our lab. He loved computer science. Not so much metallurgy, but yes, computer science. He wrote the code in Python to to identify each of these carbides and give it a color. So now we can do statistics of size, of distribution, of fraction of carbides, many things. We can test for hardness. And again, those of you who are metallurgists, you'll realize these hardness indentations are very small, right? And because the material is very hard and they're very targeted. We're not doing a hardness test over something big, but something very targeted and small. This is something we have going now, and many of you might care about artificial intelligence, or you either are excited about it or you're afraid of it. But artificial intelligence, everybody knows. So something which we've been having quite a bit of success is using these algorithms that Google uses to detect a face, right? When you do Google Photos and it can tell you from your uncle, from your friends, right? So we're using that to distinguish different types of microstructures in a weld. And this is very important. And the reason it's important is because the different types of microstructures will give you a good weld or a bad weld. When you look at it with your eye, you know it. But the computer, until now, could not do a quantitative analysis of this. So you were forced to do this by hand. And doing this painting we did here, to do it by hand, can take of the order of 1 hour using the traditional method. But now this, you realize, takes so little that it looks like zero time for us humans. So this is exciting things that we're doing. So welding has been exciting for us. We have a university chapter of American Welding Society, one for the Canadian Welding Association. If you think you might be anywhere near welding, I recommend you become members of this. The AWS, I think, is $15 American a year. Canadian Welding Association might even be free. I don't remember what their current state is. But then you qualify for scholarships. And very often, they have more scholarships than people. So I think it's a good investment very often. Our students have traveled all over the world. We've been to Bali, Sydney, crazy places. We have open labs. You're going to see our lab. And we have like many good visitors. So more things. You're going to see running message, and I'm going to say it for the first time. But for us, for me and the other students in the class, in the lab, welding is not just the act of welding, but it's an excuse to do anything else we like. So you like medicine. Okay, we can study the effect of fumes on health. Oh, you like artificial intelligence, I just showed you. You like plasma physics, we'll do it. Heat transfer, fluid mechanics, electromagnetics, anything. So a funny thing is I had a guy in the lab coming and I said, what do you like? And he said, electronic dance music. That's what he knew how to do. So I'm going to show you a quick video here before I move on to logistics. So let's see. Hold on. This is just too good, so you should hear it. So, Okay, so let's see. Volume. I don't know how you connect the sound here. Maybe one of these. If you have HDMI, you should need this. Okay, I think. So, given that it like. We have already uploaded all the material for the class. Although before each class, it's likely that we'll modify it a little bit. So if you download everything today, chances are that as the date approaches, you want to double check. The lectures and the seminars will be in this room. We'll have quite a few labs. I think it's 6 labs in here. We didn't list it as labs because if we list it as labs, then you have to pay extra tuition. But it costs me nothing to host the labs, so screw it. Like we call it the seminars, and You're going to do hands-on welding. You're going to see lots of demos of welding and of NDT. You're going to learn so much. The TAs, well, Louis is the you just met, and Mitch is the guy getting a good tan right now. And we don't need to go into every line by line. But we're going to have a seminar right after the class. This week we will have a seminar. We have the president of the American Welding Society coming to visit us. He's going to be talking about additive manufacturing of P91. So many of you said that you're interested in additive manufacturing. P91 is a material used in power, in the generation of power, right? It's a creep-resistant alloy. It's a close friend, but also very knowledgeable. So the seminar is going to be in the solarium, right? I put here where the location is, in the ETLC solarium. The class is more or less 3 parts. The first part is you have to memorize a dictionary, right? For me, it's kind of trivial. The same way you can speak your language, and the same way it's difficult to learn a new language, right? Welding has a language. MIG is not the same as TIG, and it's not the same as submerged arc welding, and a bevel joint is not the same as a T-joint. All those type of things, you have to become fluent on that. So the first part of the class is somewhat dry, because it's just like learning a new language. We're going to discuss terminology. We're going to talk about welding symbols, many things in which we will be unable to go too deep, but you will be exposed to it. And as you go in your professional path, you're going to learn different things. You're going to learn the welding processes, MIG, TIG, and all those things. You're going to try it yourself. You're going to see them in action. The second part of the class will be like, what happened here? Because everything changes. All of a sudden, we're going to start talking about plasma physics, heat transfer, energy balances, like as if it was a different course. So those of you who like to memorize will be happy at the beginning. Those who like to go deeper will be saying, oh, I cannot memorize all this. But then things reverse, right? It will be very little to memorize, lots to understand, right? And then the third part of the class, we're going to have people from industry coming and talk about codes and standards, 2 of them, one for structural and for pressure vessels. NDT, we're going to have a demo on NDT. We're going to have a lecture on NDT. We're going to have a lecture on failure analysis. And welding is so broad. We're going to go from understanding the heat transfer to understanding the fluid mechanics to understanding how you design a weld to understanding residual stresses. None of these we can go too deep in class, right? But this is the research we do. And much of the information we bring to you are things that come from either our research or the things we learn as we go to the world and learn from other colleagues. So this is very, very up to date. Sometimes it's not as perfectly organized as I would love it to be, especially the notation sometimes gets tricky. What do you call velocity? V. What do you call voltage? V. OK, fine. Let's call velocity U, right? So things like those we haven't polished yet. But what you're going to learn is state of the art, right? As of 2019. Evaluation, we have 2 groups of people here. We have the undergrads and the grads. In a very not common twist, we have more graduates than undergrads. Typically, it was the other way around. So we're going to have 2 midterms and a final. This is the way they have. But for the grad students, there will be a project. I will assign the project by Friday, September 20th. And I'd like to discuss briefly with you. But the project will be related to the class material. I care very much that you learn something fundamental and you use it, more than you talk on the surface or do a broad literature search. I care more about the understanding than about the accumulation of knowledge. Right? Here are all the dates. If for anybody, any of these dates is a problem, we have dates for everything, let me know. We have lots of flexibility, right? But especially for the grad students, these dates are hard to push because especially the date in which the project report is due. This is way too close to the date in which grades need to be turned in. So this is hard to move. All right. About the content of the exams. This is I always get asked what goes in the exam. I tell you right now what goes in the exam. Exam 1, this part goes. Exam 2, all this goes. And you're going to say, oh, it's cumulative. Of course it's cumulative, because you cannot talk about the metallurgy of MIG welding if you don't remember what MIG welding was, right? It's like learning to speak. When you go to 7th grade, you cannot forget grade 1, right? Although, of course, every new concept we learn is a concept that will be emphasized in the exam. But you cannot forget any of these, because it's building. The class builds and builds and builds and builds. So every time you come here, you have a good time, you leave. But you should never forget that it's like climbing. You climb and you climb and you climb. And one day you look down and you say, holy moly, I'm so high, right? So don't be fooled by that each thing we teach, it looks easy, but in reality we build and build and build. Book. We have just ordered these books. This book, if you go there, you can order it yourself. I recommend you don't do it, because the book is $30 US, but the post is like $40 US. And I'm not joking. Last year was like that. So we just made an order for about, I don't remember. I think we're going to have 30 books. So I'll tell you exactly. Yeah, right? We have 10. We're ordering 20.
Oh,
Yeah. So we should have books for everybody. And I'll tell you how much the distributed mailing cost is. And you can arrange with the TAs then to pay and get a book. I very highly recommend you get this book. It's a very old book. It's so easy to criticize this book. On the other hand, because it's very old, you open it up and you say, this is 1965. But on the other hand, this book has everything. And the things in which we disagree, I'm going to tell you. But it's a catalog of everything that matters in welding. And it's ridiculously cheap because it's very subsidized by the Lincoln Foundation. So this is the book that I recommend you get. With this book, you can design a weld right today. You would not know what you're doing, but with this book, you can do it. But after this class, you'll do it, and you'll know what you're doing. One last thing. We have few undergrads, but this is, and some of these might apply to the MEnGes. There are opportunities. For the undergrads, you have the DRA. I don't know if you guys are familiar with the DRA program. That's what, here you were a DRA, right? Right, and in which if you get on board, here is the link. At the end of the semester, the dean pays you $500. You make a poster of your presentation. But the real deal is that you would have spent time in the lab, hanging out with the grad students, learning, making friends, making connections. And if you don't like it, you take the $500 and you leave. And if you like it, that's how we get our grad students, right? If you don't have the GPA, or for any other reason you wouldn't do a DRA, you can volunteer. We have lots of volunteers in the lab. And it's just the same as a DRA, except the dean doesn't give you $500 at the end of the semester. But I welcome. When I welcome people to the lab, I don't care about your GPA. Can be super high, can be super low. All I care is that you have a good heart and an open mind. You don't even need to be a genius. I don't care. But if you have a good heart and an open mind, you start making progress. And then, because we have such an amazing network of good people, we build on it. And you do so much more than you ever thought was possible. And not to mention, we have $5 million of facilities in which we can do pretty much anything we want. For those who very often, especially the undergrads, ask me for summer projects, I tell you right now, you can apply for this NSERC USRA, in which they will pay you a reasonable stipend, right, to do work in the lab. So that's another avenue. I think I have to top it up a little bit, so we should discuss if that's something that interests you. But there are many opportunities. Here are some of the topics, but I'm not going to dwell on these too much right now. From metallurgy to control to physics, anything, electronic dance music, anything. For both undergrads and grads, there are these travel scholarships, the green and gold. So these are good if you want to come to the, for example, the American Welding Society trade show, FabTech, that is in November. I think for this November it might be too late. But you apply for this, and they pay 80% of the cost, up to $1,500, right? And you get to go to a conference, network, meet people, make friends. So I recommend those things. Any questions about logistics? Any questions about logistics? All right. So now let's talk about something meaningful. So. Okay. So what is welding engineering, and does it matter at all? So I uploaded a bunch of material already on the website. There's a paper I wrote on this. People seem to like it. It's not a scientific paper, but the paper is much about what I'm discussing today. And I uploaded some supporting material, like the welding of the Saturn V rocket, or some information about the T-34 tank, or other things that are pretty cool. So what is welding engineering? The class is on welding engineering. This is not teaching welding. And Sven, you can disagree with me as I present here, because I am giving my spin on this. But let's start here. Everybody knows what a welder is, because you see the guy with the spark welding, right? Now, not everybody realizes that there's much more than that, right? So I came up with an analogy between welding and music. So a welder is like a musician. So here you have Paganini, who was a violin player, very, very famous. He was so good that people thought he had a pact with the devil. So when he died, people refused to bury him in a Catholic cemetery because they thought like he had made a pact with the devil and couldn't go into a normal cemetery. Anyway, he didn't care because he was already dead. So has an awesome ear, has an awesome hand. That's a musician. That's a welder. Now, in music, just like in welding, there is more than that. So the equivalent, somebody had to make the instruments for Stradivari, for Paganini to play. And indeed, he owned a violin by Antonio Stradivari, right? Like the Stradivarius violins, right? Now, Antonio Stradivari, nobody knows if he was a good player or not. And nobody cares. But his violins are sold by millions and millions of dollars, right? So now what I want to bring to your attention here is when we say welding, people think welder. And if you tell any of your friends you're taking a welding class, they say, oh, are you learning to weld? So the answer is no. But what we are learning is how the instrument is made, right? In this case, it's a violin. In other cases, in our case, is a welding machine or a welding electrode, right? And our lab looks just like this with the muses and the light coming through the windows. Huh? So first important aspect, you have the welder and you have the welding engineer. And you need both, because this guy with the violins, nobody would have known if he was a good musician. And at Stradivari, nobody asked him, hey, you're not good enough playing. Why do I care, right? Like I'm good at making violins. There is something else that the welding engineer does, and is composing, much like Mozart was a composer, right? And everybody can know melodies from Mozart, right? And what is the composition in welding? That's when I mentioned the welding procedure, right? The welding procedure is like a music sheet. The music sheet says, oh, you have to take a do, re, mi, whatever, whatever, right? And the welding procedure says you weld with this current, with those many amps, at this velocity, with this electrode, right? It's much the same as a music sheet, right? Somebody has to write that music sheet, right? When the things are of high responsibility, you need a professional. That's the job of a welding engineer. When you need to weld that chair, maybe nobody cares. You just go and weld it without a written procedure. Now, these three things they don't have rigid compartments. For example, Mozart was also an amazing player, right? It's like being a welding engineer and being a welder too. You can be both, right? But you have to realize you're both. It's not that it's just one thing all jumbled up. Also, some people were like good musicians and good instrument makers. Brian May of Queen, he made his own guitar, right? Anybody knows that? The Red Special, right? He made his own guitar. So you can be both, but you have to be clear. Welding is one thing, the act of welding. The act of making the instrument is another thing, and the act of saying what the instrument should do is another thing, right? We live here. This class is about this. You're going to have like about 3 hours with the electrode in your hands. That's this. But so you have an appreciation. You're not going to get any good at that. Maybe unless you're naturally talented. But with this, you're going to get pretty good, right? Now, why do I say all this? This is my daughter. She took a 1 day of welding lessons in St. Joe's School. It's a high school here that has a welding program. And she learned to weld. I don't think she's going to be welding pipelines. But she learned to weld. And that's on the day she was learning. And the jacket is way too big and everything. And now I have to put up with my own daughter that says, I talk about welding, but she knows welding. So now, before you say that I talk about welding, but I don't know welding, for example, Sven would say that, but I already made my preemptive strike. So, okay, welding. So now that I explained welding engineering, does it matter? Okay, let's see. How about if we don't know welding engineering? We can have bad things happen. This is the Alexander Keelan platform. So this is an offshore platform that collapsed. Lots of people died. More than 100 people, it's hundreds of millions of dollars, really bad things. Bad, 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 bad. Why did it collapse? Well, guess what? This is the platform, these are the pontoons, and these are the columns that support the platform. This is load bearing. This is load bearing. This wasn't load bearing. This is just a thing like connecting the arms. The load is vertical. Now, somebody decided to put a hydrophone here, a transducer. They just welded it. What's the big deal? Well, what happened is that this, because it was high carbon steel, and you're going to see that that's a bad thing typically, developed a crack. The crack went through this support member, opened up, and then, it doesn't appear here, but this arm opened up, and the whole thing tipped over and fell, and everybody died. Well, maybe somebody was rescued, right? But isn't that crazy? Just because somebody was welding a microphone there, 123 people die. So does welding engineering matter? I would say it matters, at least for those 123 people. They would be around with us today if they had thought that this combination of electrode and welding was going to be a problem. Everybody knows this, right? Like the Liberty ships that were built during World War II in massive scale to transport cargo across the Atlantic. They were making them, I think, in 24 days, each ship. 24 days to do a whole ship. But the ships had problems. Many of the problems related to the welding, right? I read it somewhere, and I couldn't find it today, so I need to make sure this is right, that more of these ships sunk out of structural problems than out of torpedoes, right? These ships would crack, like this one. There were many things, but one of the things is they had a stress concentration around the welds, right? And at the time, people didn't understand really the issues of the relationship between toughness and temperature of the steels. What enabled these ships to be built so quickly was welding. And you get to see again, you didn't understand enough welding engineering back then. And you see what happens. Now, this is when you don't understand welding engineering, but if you know welding engineering, good things can happen, at least if you're German, like Sven, right? So this is the graph space. Any of you has learned an interest in World War II? No? Okay, it's fascinating. So this ship was built between the two world wars. After Germany lost the World War I, they had the Versailles Treaty that said you can only make Mickey Mouse ships, right? They said very small. And at the beginning, they were trying to toe the line, right? Eventually, Adolf Hitler said, screw it, and started to make Bismarck and all kind of crazy things. This ship was done within this treaty in which they were supposed to make ships that were so tiny that were like harmless. But the Germans decided, how about if instead of riveting the ships and having the overlap of the plates, we weld the plates. And if we weld the plates, now I'm saving all this weight, and I can make a much bigger ship, right? And they welded the ship. And when the World War started in 1939, they sent this ship to raid like the planet. The British didn't know where this ship was. They sent 9 fleets, 9, to chase after this one ship, right? They finally found it like right outside Argentina. And it was this ship and the tender ships, the ones that bring the supplies, against 5 British ships. Okay, let me tell you, the British ships won, right? And these guys made a terrible mistake of trying to find refuge. They went to Uruguay instead of going to Buenos Aires. It's not a good thing to say, but at the time of the war, the Argentinians were kind of more friendly to the Germans than to the others. And instead of coming to Argentina, they went to Uruguay. And Uruguay said, okay, you have to leave within 48 hours or something like that. So the captain killed himself. They scuttled the ship. It's still today right outside Montevideo in Uruguay. They did it in shallow waters, which was stupid because the Americans came. This is the telemetry and has a special radar to the ship at the beginning of the war. And they could come and get some of the secrets. But the ship's still there. Just think of this. They welded the ship, and they needed 9 fleets to come chase after that. So just as when you don't know welding is bad, when you do welding, it's not that bad, at least for the Germans, right? But not only for the Germans. T-34 tank, right? T-34 tank is a super big deal in the Soviet Union. So the Battle of Kursk was the biggest tank battle in history, right? Lots of Panzer tanks, lots of Soviet tanks, T-34s, right? The Soviets won, right? And it was the beginning of the recovery of the Soviet land. According to Wikipedia, which never lies, the statistic is that each Panzer would kill 7 T-34s. So you would say the T-34 sucks. Well, except that the Germans were welding the tanks by hand, and the Soviets were welding them using submerged arc welding, something which you're going to learn plenty and see it in action. And they could make these tanks in an automated way with a relatively good quality, right? 7-1. So it's not if the tank sucks with a 7-1. It's can you make more than 7-1 tanks? And they did, right? And they won the battle. This tank, the engineer in charge of this was Evgeny Paton, right? And he was named like the director of the Council of Sciences of Ukraine. It's like our NSERC. So all the sciences, not welding, not metallurgy, all the sciences, physics and everything, the director was the guy who did the welding of this tank. Super big deal, don't you think, right? So again, like welding is so much more than the act of welding and has been so crucial in shaping civilization. Outside wars, right, World War II, welding is essential, for example, for aerospace. This is a jet engine, right? This is a passenger jet engine. Some parts are hot, right? You have a combustion chamber. Some parts are cold, where you have the fan at the beginning. So the materials you use for one or the other are not the same. So, for example, the shaft. How do you connect a shaft that made with some materials for cold with the shaft, the part of the shaft made with materials done for hot? You have to somehow weld it, right? And that's, you do it by friction welding. Whatever it is, we're going to get into that in detail, right? Airbus 380, right? Super interesting. Remember when I mentioned here the Paton, Evgeny Paton, and there is a Paton Welding Institute, was largest in the world. After the fall of the Berlin Wall, like all these Soviet people didn't know what to do. Well, they were stolen by Airbus. And it was the people from Patton Welding Institute that were taken to France that developed the laser welding for this plane. Passenger planes are not welded, are riveted for many good reasons. But for even better reasons, Airbus decided to weld it. Because if you weld it, we go back to the Graf Spee, the German ship, and you can make it lighter. And that's one of the secrets to make this enormous plane, welding. That's with lasers. F-22 here, this is a titanium, the plane is made out of titanium, and the whole aft section is welded, right? Jet fighters tend to be welded, right, with electron beam. Titanium is reactive to oxygen, so you do electron beam that is in vacuum, and there you go. Friction stir welding, whatever that is, but one of the co-founders of Microsoft, or one of the first employees, had so much money and said, let's make an airplane in mass production the way we make cars. And one of the ways they wanted to do it is by using a special type of welding, friction stir welding, which we're going to show you in the lab. And this airplane, despite it's a jet plane, has the price tag of a propeller plane. Look, more aerospace. Saturn V, right? They almost missed the window of putting a man on the moon before the end of the decade. They did it in July 1969, right? They almost missed it for two reasons, on the second stage both. One, they had a problem with the thermal insulation. The other problem is they had problems with welding. And I uploaded the articles about the welding of the Saturn V written by the engineers that troubleshoot it, right? Super interesting. So who knew, right? Like welding so critical. Rockets, like the Delta rocket or the space shuttle that now is not in use. People decided that if you mix aluminum with lithium, the aluminum is lighter. So all the weight you can put inside the shuttle, it can be useful payload. The problem is now that alloy doesn't weld. When you want to put it together, it curdles like milk, right? So what do? Well, they developed technologies, among those this friction stir welding, to weld this unweldable aerospace alloy, right? Crucial. It's so essential. So again, the message here I'm trying to convey is that when you say welding, the first image in your mind is a guy with little to no education holding a torch and lots of sparks and fumes and ugly things. That's true, but it's a part of the truth. There's an enormous, bigger part of the truth that says, oh, they almost missed the window in the Apollo mission. They had trouble with the space shuttle. The Germans had an amazing ship. The Americans had a bad ship, right? Like all those things came down to welding. Cars. Why aren't there aluminum cars? There are many reasons. One of the reasons is they're very difficult to weld. You weld them in a completely different way than a normal car. Now, this is a funny anecdote because Tesla cars used to be all aluminum, right? The Model S, the Model X, right? And that's awesome. Okay, they were making aluminum cars. Then they said, let's do the Model 3. And you know that the Model 3 was delayed, right? You know that it came super late into the market and was big pain. And you know why? They couldn't weld it. And the funny thing is they were making aluminum cars that are so difficult to make, but they had no experience in making steel cars, which everybody knows how to make, but everybody who makes cars like Ford or whatever, they had like decades of experience. They had zero. They had to learn from scratch, right? Welding. So you read about Elon Musk and all the crazy tweets and everything, and many things came down to welding. Oil sands, all these trucks, all welded. Super important things. Pipelines, buildings, offshore platforms, right? And this next photo, I took this one. Did you know that a cast sculpture is actually welded? Did you know that? When people say this is cast sculpture. Okay, cast is putting the molten metal in a mold, right? And I always thought that if they were making a horse, that is the case here, the 4 legs. If you're making a horse, you make a horse in clay, you make a mold, and then you put the metal. No, it's never going to work. So when the artist makes the thing in clay, somebody comes and cuts it up in pieces. And I saw this. I took this photo. Cuts it up in pieces, and they cast this piece independently. Then a guy welds it. He's welding with TIG, whatever it is you're going to learn. And the super crazy thing, in this particular case, horse. The horse has hair. But when you weld, you don't weld with hair. So after this guy welds, another guy comes with a Dremel tool and makes hair by hair, like doing the scratches with the Dremel. And now that I tell you this, if you go and see some bad sculptures out there, you're going to see that in some of those, you can tell the welds, because if the alloy is not perfect, it's going to have a different oxidation than the rest of the alloy. And you can see the difference in color where the welds are. Typically you don't, because I pay a lot of attention. But sometimes you do, and it makes me cringe. So the impact of welding is huge in the US, even huger in Canada, and mostly because Canada is a natural resource-intensive economy. We better change and get up our game, because we're going to turn into Africa otherwise, right? Like if we just export natural resources. But for natural resources, you need to weld the machines, to maintain the machines, and the pipelines, and the wear-resistant materials, and all those things. So there's more expenditure per person or per household in Canada than in the US. Interesting. So I want to tell you, and I have about 10 minutes, something about welding being an art. People say welding is an art, right? And people say, welding, what do you need to know? I mean, haven't you made buildings? Haven't you made bridges? Haven't you made cars? Why do you need me? Well, I still like my Joe. So I'm trying to justify why, despite that we do have cars and airplanes and bridges and everything, in welding we're only starting to know what we're talking about, right? And welding is an art just like music is an art, but making the instrument is a science, right? And better than science, I'd like it to be an engineering. And engineering, we have the art, we have quite a bit of the science, and very little of the engineering. That's my calling in life, and that's what brings you here. So, look, any of you heard of the movie Fantastic Voyage? No, young people. So it's a movie in which they make a machine that shrinks. Have you seen that movie, Fantastic Voyage? They make like a submarine, and then they shrink it and they put it inside the vessel to fix a brain tumor, right? Like a precursor to nanotechnology. So let's do this. Here is a welder, the way everybody sees. Here's Joe with the torch and the smoke and all this stuff. That's what everybody else knows, and this is what you knew before you walked into this room today. But if we go closer in our fantastic voyage, right? Here's Joe. Here's the weld, and you see the sparks and all that kind of thing going on. You see the guy with the mask. This you already know. I'm not teaching you anything new. Okay, let's get it a little bit closer now. Now, what you see here is what the welder sees. What do you see? This is the base plate here. Here we have the weld, right? And here you have molten metal, which we call the weld pool or weld puddle. Here you have an electrode. You have this big spark, which we call an arc, right? We're going to talk so much about this. So all this is going to be like trivial to you later. Here we have another image. This one is from our lab, right? Another type of welding, right? But in electrical welding, you always see the same thing, right? In arc welding, you have an electrode, you have a current, you have the molten metal here, you have this thing, this arc, right? This is a frame from one of the previous videos I showed you, right? And now I have a question to you, because this is interesting. In welding, we have electricity. We have the electrical current. But the electrodes are not touching. So how does it work? Because I have an electrical outlet right there, and I'm passing my hand very next to it, and I'm not getting zapped. So why is electricity not jumping to me, but the electricity somehow is jumping between the electrodes? This is a very important question. And it has a straight answer, of course. What happens is that in this arc, right, in the gas between the electrode and the plate, the atoms and the outer electrons are separate, right? Typically, an atom is electrically neutral, but you can make it lose the outermost electron, right? And now the gas starts to behave somewhat similar to a metal, right? In a metal, right, it conducts electricity because it has this cloud of electrons around it. So a gas is not like that unless you can make it happen. And the question is, why is the electrons loose, right? And the answer is because it's ridiculously hot. How hot? Very, very hot. An arc is 20,000 Kelvin. It's a huge number. I mean, you don't want to touch it. But if you think the surface of the sun, that's 6,000 Kelvin. And now I'm telling you something, right? Because the guy without education, with the smoke and the mask and all the sparks, is holding something at the tip of the electrode that is 3 times hotter than the surface of the sun. There are very few places in the planet that are at that temperature. And those other places are other welders around the planet welding at the same time, right? So if this doesn't explode your mind, I don't know what it will, right? And now, when you think you know everything about it, do you know everything about these plasmas at 20,000 Kelvin? So how does it get to be so hot? You might have heard about Joule heating, right? If we have current, the current has resistance as it goes through the gas, so it generates heat. And this heat is enormous. This heat is of the order of like 1 to 5 kilowatts, right? If you have an iron and you're doing a shirt, that's about 1 kilowatt, right? Now the difference is this can be like 5 irons and on something that is 300 times less area, right? No wonder you melt metal. One of the reasons welding is a modern process. Like 200 years ago, you didn't have this type of fusion welding. And it's because you couldn't concentrate the heat so much to melt the metal. If the heat is not intense enough, the metal sucks it up and diffuses it without melting, right? But this is what we accomplish with the arc. Let me tell you more. Electricity causes motion. You know this because electric motors work with electricity. Somehow you put current and you get a motion there. What you might not know is that you have just a similar engine inside the weld. So I'm not going to get deep into this right now. And I understand that few or none of you took a class on electromagnetics. Anybody took a class on electromagnetism? You did? OK. But your major is, what is it?
It was mechanical.
Mechanical. OK, good for you. I'm a mechie too, and I took a class. So when you have a current, you generate a magnetic field according to the right-hand rule. Now, Faraday's law says, that's Faraday. So Lorentz law says that if you interact the current and this magnetic field, you generate a force. That's the force that makes a motor move, and it's the force that makes a transformer buzz, right? And if you do it and you do the calculation, you're going to see that this circle of magnetic field creates a pressure in here. And the smaller the circle, the higher the pressure. And the arc opens up like a bell. So here it would have high pressure. And here it would have low pressure. And guess what? Right? This more pressure on the top, this pressure differential, you do Bernoulli, and pretty much dead on, you get a velocity of the plasma. And what is this velocity? The velocity is more or less 300 meters per second. 300 meters per second, again, whatever that is. By normal passenger plane, right, is flying at 240. Right, 340 is the speed of sound at room temperature, right? This is not supersonic because it's above room temperature, right? So, Mr. Joe, with second grade finished, and a torch in the hand, and probably a cigarette, and the mask, and the sparks, and the smoke, and everything, he's holding something that is hotter than the sun and faster than a jet plane. I think that's cool. And he has to control that. And all he knows is it works. Now you're an engineer and you say, oh, let's try this new alloy. It might not work. You're an engineer and say, let's try using more current or less current. And then things happen. And they are not always the good things that happen, right? And then you realize that you have like so many variables to play with. Who tells Joe how to deal with this new situation? typically, you start trying everything like a monkey. You call yourself a welding engineer until something works and you're happy you've solved the problem. And next time you have the same problem or it's slightly different. And you go monkey mode again, change everything until something works. My hope, as I teach this class, right, and as we do our research, is that we're going to have a level of understanding that may be continuously increasing, such that when we have new alloys or new machines or new problems, we're going to reduce the monkey stage smaller and smaller, and the real engineering stage larger and larger. This is a good hope for us, because in the whole world, we go trial and error. So if we want to be competitive, this little bit of knowledge is something that gives us a leg up, right? So, look, I have, I think, a couple of slides to finish. This field of the combination of electricity and magnetism and fluid mechanics, this is called magnetohydrodynamics. That is an awesome word to drop at parties, right? And the guy who started the field is Hannes Hofmann. And he got the Nobel Prize in Physics in 1970. He's one of the very few engineers who got a Nobel Prize, right? And he was studying the surface of the sun, which we know is a third of the temperature of a weld. We're so much cooler, we're so much hotter, right? So I'll keep waiting for my Nobel Prize call to arrive anytime, right? This is not for whims. Of course, we're not going to go as deep as this guy went in the class. But you start to see that Joe might or might not know that he's dealing with some like very powerful forces of nature. Deep, deep stuff, powerful stuff, that if we know how to handle, we can do amazing stuff. So this fast plasma, these photos are from my PhD thesis, right? If you have this fast jet, you can blow your molten metal away, and you get a defect like this. This defect, for those of you native English speakers, this is called humping. And everybody cracks up when I say that I did a PhD on humping, right? And but we got to understand it, right? And there are more things about the electrode, but I want to finish with one thing. Welding is super interdisciplinary. So I mentioned to you about the plasma, right? About the math that is associated with that. That was good enough to earn a Nobel Prize to a guy. If you're mechanical engineer, solid mechanics, right, matters. The automation. You're a metallurgist or a chemist. Oh, you have chemical reactions all over the place. If you're an electrical EE computer guy, controls, power supplies, big deal. You're a civil engineer. Okay, how about welding the steel structures? What are the issues of corrosion, fatigue, strength? You want more. How about non-destructive testing? How about the economics? How about the logistics? How about the business aspect of this? This is like no end to it in welding. You said you wanted to spend your life learning. Well, let me tell you, if you start in welding, you're going to die, and you would have learned like this little thing, right? And in next class, I'm going to give you an introduction to welding and start talking about joining in general before we start discussing the particular aspects of welding. So I hope this is an appealing introduction to a field that I love very much, and I look forward to seeing you next Thursday then. Thank you very much. Let's start and stop here.